Okay, so here's another 3-point mapping cross. I don't think it's overly relevant that Priscilla and Margaret did this experiment, although it is good to remember that these things are done by people. And so in this case, we have 3 genes in mice. I guess it's good that we're doing something other than flies for a change. And I'm going to probably, as I go through it, I'm going to call this M, A, and R. When R is dominant, it looks like, so that's important. It doesn't really matter that much. So they carried out a series of 3-point crosses mating mice that are heterozygous at all 3 loci with mice that are homozygous for the recessive alleles at these loci. The fact that it's dominant doesn't really do anything. It doesn't mess it up at all. All it means is that we're going to have mahogany over plus, goody over plus, and R over plus. And we do a test cross. The only thing it changes is that we would do a test cross with something that's like this. So, because in this case, R is dominant, so plus would be recessive, and I just know that because I gave it a big R. But it doesn't really matter. The numbers all end up the same. So we just analyze this one the same we do all 3-point crosses. The good thing about this section is once you know how to do a particular type of problem, when you see that problem, they're all the same. But you just have to get practice doing them all. Alright, so I can look at this, and let's see what we got. Well, let's see, these are the most. So those are the parentals. These are the least. So these are the double crossovers. The rest of them are some kind of single crossover, and it's going to be a little bit tricky to know how to group these because we've got these guys and these guys, and we got these guys and these guys. So we'll have to see how that looks. So first of all, our parentals say that A plus and M started out on the same side, and plus R and plus started out on the same side. Our double crossovers are A, R, and plus M. We look up here, we try to see which one jumped to which side. Okay, so another 3-point mapping cross. I'll try to go through this one relatively quickly, and hopefully you guys can start to do them pretty quickly yourselves. So here we go. The first thing to do, what I like to do first anyways, is to identify the parentals, because that tells you what's going on. So our parentals are these two. That means A plus and M. I'm just going to use M instead of MG and R instead of RG. So A plus and M started on one side, plus R and plus started on the other. Our double crossovers are the fewest, so the double crossovers are A, R, and plus, and M. Alright, so what had to switch sides? So these are parentals, these are DCOs. What had to switch sides to change from a parental to a DCO? We can kind of go through them one at a time. So if A switches, then A comes down here and is now going to be AR plus. And that's what we got. And plus goes up top, and then it'll be plus M and AR plus down here. So that tells us the order. That tells us that A is in the middle. And if you can try each other one, if R switches and R goes to the top, then it would be ARM. If M switches and goes to the bottom, then it would be A plus plus on the top plus RM on the bottom, but that's not what it is. So these are our DCOs, these are our parentals. By looking at the parentals and saying what happens after a double crossover, that tells us what's in the middle. So that tells us A is in the middle. So we're going to rewrite it with A in the middle. A in the middle, and then it doesn't matter what goes on either side. you have to make sure that M is over plus and R is by plus and A is across from plus. Okay, so that's awesome. So now, that's the hard part. So the hard part is figuring out what order they're in and what's on which side of the line. So now a single crossover between plus and A, or between the R and the A locus, will give us plus, plus, plus. So this is a crossover between R and A, so a single crossover. And then if we got R crossing over to AM, we would get RAM. So how many of those did we get? If we look over here, plus, plus, plus is 16. Oops, 16. RAM is going to be this one, RAM, so 36. And always put in the double crossovers. And the reason we do double crossovers is, I'll show you here, we get plus AM over R plus plus. What we're trying to do is number of recombinants over the total. So we want to know how many recombinants occurred, how many times did recombination or crossing over occur between plus and A, or between R and A. Alright? And so if a single crossover goes over there, we want to count that. But if we get a double crossover includes this and includes this. So that's also including a crossover there. So don't even worry about it. Just always add in the double crossovers. Then the next one. So what's our order? Our order is over here. I'll rewrite it because it gets pretty sloppy there. Over R plus plus. Now we want to look for crossovers here between A and M. If we get a crossover there, we go plus A and come down and get a plus. We go R plus and come up and get an M. So that would be plus A plus R plus M. How many of those do we get? So this A plus plus is the same as plus A plus. So we're really thinking of the phenotype. So really the phenotype would be a Goody. And this other one down here would be R plus M. And so that would be ragged and mahogany. But how many of those do we get? We get 15 plus 9. Always throw in your double crossovers. And there we go. Add these up. We get 26 plus 2 is 28. No, 15 plus 9 is 26 plus 2 is 28. Handy dandy phone over here. It is 15 plus 9 plus 2 is 20. Oh no, I guess that's 26. My math was off a little bit. Divided by the total. So the total is 223. And that's 11.6. So now our distance between R and M, no, I'm sorry, our distance between, which one are we calculating here? That was this guy, so this is between A and M. That's where we're getting the crossover. That distance is AM is 11.6. And then the distance between R and A, that's what we did up here. So that's 36 plus 16 plus 2 is 54 over 223. 24.2. So it's 24.2 away from A. Where does it go? Does it go down to the right or does it go down to the left? When we do 3-point mapping like this, we're going to know this goes to the left because we know that A is in the middle. And that's kind of the trick. That's kind of why you do a 3-point cross, because you can quickly tell what's in the middle. All right. As my biochemistry professor, Dr. Chen, used to say, couldn't be simpler. And pretty much every time he said that, it could be simpler. But I like to say it anyways. He used to say, couldn't be simpler. And he used to say, lo behold. So I'll try to throw a few lobe holds in there when the opportunity arises. All right, so fine spines, smooth fruit. How does TU mean smooth fruit? Doesn't make any sense. Uniform fruit color. There are 3 recessive traits in cucumbers, the genes of which are linked on the same chromosome. A cucumber plant heterozygous for all 3 traits used in test cross, and the following progeny are produced from this test cross. Oh, and they're not in order this time, so they're making it tricky. So we want to do the start all over again. All right, let's go fast. Parentals. That means that little s, little u, big T go together. Big S, big U, little t go together. DCOs are big S, big U, big T. So that's the 2. The 4 are little s, little u, little t. So those things have to match up. We have a big S, a little s, big U, little u, big T, little t. If the T switches, that the big S and the big U and the big T are all together. So that makes sense here. I know the way this worked out, I now have big S, big U, big T on top, but that doesn't matter. We're just saying what, actually, this doesn't even have to be there. We're just saying what kind of gametes would we get from a double crossover. And we can tell, so the way it's lined up now, if we got a double crossover, the U would switch sides. So we have it lined up the wrong way. We have to get T in the middle. And we know that because to go from our parentals to our DCOs, it looks like the T's switched. So let's try to write that and keep it right this time. Well, I just said the T had to go in the middle. So, T in the middle. Little s, little u. Try to make them obvious. Big S, little t, big U. Little s, big T, little u. And I'm just writing it twice so that when we do the crossovers it makes sense. And we want to look for our crossovers between S and T, and our crossovers between T and U. Go with green first. Little s, little t, that's a big U. So little s, little t, big U. Big S comes up here, gets a big T and a little u. Big S, big T, little u. This one, we're talking about a crossover over here. So we would go little s, big T, big U. Little s, big T, big U. Big S, little t, little u. Big S, little t, little u. Little s, little t, big U. Little s, little t, big U. That's one of our 21s. 21. Big S, big T, little u. Big S, big T, little u. That's our other 21. Always add in the double crossovers. And the other ones, again, now I used my 21s already, so I know that the next ones have to be 13 and 17. They're kind of lumped together. 13 plus 17 plus 2 plus 4. And again, the reason I know that is that they're the only numbers left over. But we can double check. Little s, big T, little s, big T, big U. Little s, big T, big U, that's our 13. Big S, little t, little u, that's our 17. So 17, 13. Then we can add all those guys up. We can make our map. We know that T's in the middle. So we'll go T to U is 13 plus 17. 13 plus 17 is 30. Plus our double crossovers, which are 6. It's 36. Divided by 230 is 15.6. So T to, which one we were doing? That was our T to U distance, so I did that one first. And so that's 15.6. S is down here. That's going to be these guys, our distance between S and T. So 21 plus 21 is 42. Plus 6 is 48. Divided by 230. 20.8. And that's our map. Now you see a lot, oh, I should have said, lo behold, there's our map. Couldn't be simpler. It could always be simpler. There are other ways to do these. I think we'll just stick with this way. If you look at the link to, so I linked to an older genetics textbook that's like a really good old genetics textbook. And so on our course web, there's a link to a book. You can actually go and look at that whole book at that site. And it shows a slightly different way to do it. But however you do it, as long as you end up with the map, that's good. All right, so that's it for 3-point mapping. I want to show you a couple of things. I'm going to OneNote, and I just want to talk a little bit about what's happening with the chromosomes when we do this. So let's say, so all we're really doing is we're doing our chromosomes are going to look like this. And they're going to have some genes on there. And let's put A, B, C. So when we do these problems, we don't always show all of the chromosomes. So this would be an ABC over plus 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 heterozygote. And we want to think about what kinds of things we get out of it. So our parentals are ABC. So if no crossing over happens, we get ABC and plus plus plus. So just like before, these are our parentals, which are our non-crossovers or our non-recombinants. And those are the only ones that are non-recombinants. If we get a single crossover, so we'll do this on a couple pages. If we do a single crossover, again, we'll do this in green. We'll always get parentals out of it. And so we talked about that every time you get a crossover, you're always going to generate parentals as well. So that goes into the thinking that when we look at our recombination frequency, we're really underestimating how often crossing over actually occurs. But it turns out that if we just do the maps the same for all the time, then we're using the same basic units. So we're just interested in what kinds of recombinants are generated. And so if we have a single crossover here, we got little a, comes down and crosses over down here, get plus plus. The other one gets a plus, comes up, BC. Start out with a plus, get BC. So these are single crossovers between A and B. And you would get slightly different things depending on what order you put them in. So that's how you get a crossover here. Little a, little b, plus. Little a, little b, plus. Plus, plus, and c. Plus, plus, and c. Alright, so that's good. Now we just have to do a double crossover. So these were single crossovers between B and C. Oh, let's do our double crossovers in red. It's dramatic. This takes some practice. This does not come immediate. So, plus, crossover, pick up a B. Crossover, pick up a plus. Plus, B, plus. Yeah, let's change colors again so you can follow this one a little bit better. A, crossover, pick up a plus. Crossover, pick up a C. A plus C. And so this is a situation where, so we're swapping the middle of the, so this is what we say when, so remember our parentals were A, B, C over plus, plus, plus. And the one in the middle, switch sides. So when we do the problems, we're looking at the double crossovers because we know that a double crossover causes things to switch sides. And so we can say, okay, when we did the double crossover, it switched. The thing in the middle must have switched. And so that's the chromosomes. And so these are double crossovers. But a double crossover includes a crossover between A and B and a crossover between B and C. So when we're totaling up how often we get crossing over between each pair of genes, we have to include them. Alright, so that is about all I have to say about 3-point mapping for now. So, have a good one.